In this video, we're going to cover the fundamentals of functions and relations, but before that, we're going to address some student questions. Enjoy! We've hit time, let's start. Cool. So this class will be eventually going through the chapters 5a through c, so some functions and relations fundamentals. First things first, I'm just going to get through a student question, namely, how do we handle the solution for circular functions when it can only ever equal something that isn't quite an exact value? This does have a very easy solution, and that is that you can only solve it with the CAS. That's literally the whole thing. So, bit of an anticlimax there, but that is just unfortunately the case that you have. So, as far as how you actually do solve those, I'm just going to go through menu 3.1 if you're using TI Nspire, or I think it's Math 1 for the Casio. You put in your sign, so sine of 2x in this case is equal to negative 0.8, and you just put your domain associated with that. So 0 less than equal to x less than equal to 2 pi, because that's this portion here. You want to solve between 0 and 2 pi. You'll find, oh, what did I do wrong? Oh, didn't solve for x, comma x. You'll find that if you try to get an exact value, you'll get like the inverse cosine of another value. That doesn't actually have an exact form beyond what you're seeing there. So when you do your control enter, that's what you end up with. So all these values are, all these values are in terms of radians. So if you think about 2 pi being 2 times 3.14, you're basically capping out at like 6.3-ish, which is why this number doesn't get beyond 6.3. So yeah, in short, if you have some weird wacky decimal and there's no way to make it look like either 0, half, root 2 over 2, root 3 over 2, 1, any of those exact values that appear on the unit circle, then it's just going to be a CAS question. Does anyone need to see me do this on the other calculator, or is it fair enough how we approach that?
Hey Chris,
Hey.
sorry, just joined a little late. I think
Yep.
I just missed the start.
Yeah, so this was just a quick student question. It was essentially what happens if you have a circular function that doesn't equal an exact value. This just ends up being a CAS only question. So I've just shown how to solve that on the CAS. Do you need to see that in any more detail?
I don't need to see more. It was just you know how after the brackets you put like a straight line,
Yep,
and
yep,
then you put like the restrictions on x.
yep,
How do you get that line, like, or where do you get the line from?
yep. So if you're using this CAS, it is control on the equals. So if I zoom in there, you'll see, yeah, there we go, it's focused in. It's this right here. So if you control and do equals on the CAS, you'll see that line is in the bottom right hand corner.
Yeah, all good.
This is the CAS you use, yeah?
Yeah, that's the one that I use.
Easy. Yeah, so if you're not using that for anyone else, it'll be in the Math 1, 2, or 3 menus. It'll be somewhere in there, I'm sure. Okay, that is that. Moving on to the content for today. We're looking at set notation, or at least chapters 5a through c here, doing some functions and relations fundamentals. So, you've actually already seen a quick introduction to set notation, namely, if you go back to the handwritten bit, this E here, this element, and these brackets, this is all what's part of set notation. So we'll just do at least a brief overview of all the possible symbols, all the possible sets, and if I need to go in any more detail, you guys just let me know. Okay, so first things first, we use this element symbol to say that the thing on the left belongs to the set on the right. So when we saw in the handwritten bit, I said theta is an element of 0 to 2 pi. It just means that my angle theta belongs to the set that is described by all the numbers between 0 and 2 pi. One example they've written here in English for some reason is 2 is an element of the even numbers. because it is, in fact, an even number. If something does not belong to the set, then you could say x is not an element of that set. So 2 is not an odd number. That's one way of doing that. You'll see later on there'll be like this set difference that you could use instead, which is a bit more common. As far as subsets, you can think of these as sets within sets. So if you imagine A is everything included in the red, so the 3, the 4, the 0, the 1, the 2, that is all of A. But B, all the numbers that are specific to B as well, are fully contained within A. And so because everything in B is fully contained in A, we call B a subset of A. And the way that's written is with this like sort of upside down union symbol. So to write that out a bit, maybe a bit clearer in the handwritten bit, you would say B is a subset of A. So it's kind of like a C with an underline on it. Apparently you can also say this as B is contained in A. Whatever. Okay, that's that. A few other things, namely the intersection symbol. So you might have learned this from when you first looked at Venn diagrams, which was you would have, yeah, actually if we just go back to the screen share, you'll see you've got a Venn diagram A and B. This bit in the middle where the two circles intersect, everything in here is described by this like sort of N looking symbol. It would be described as A intersect B. You can write that either way. You can say A intersects B, or you can say B intersecting A. It's the same thing. What you could say if you had completely disjoint Venn diagram, so if I draw one of those up, you have set A over there, you have set B over here. There is no touch, there is no intersection between those two things. One thing you could do to say, like if you're told to solve what is A intersection of B, you say it's the null set, which is a 0 with a slash through it. They've called it the empty set in this book. Null set is also appropriate. As for a bit more terminology, these would be considered disjoint sets if they have no intersection. A lot of this is going to be terminology. Okay, the union, so A, U, B, look a deep U looking shape, that's everything included in your Venn diagram. So A union B would become 1, 2, 3, 4, 5, 7, and 9, all those numbers. That is the union. Now, the reason why it gets its own little thing, rather than just being called the join of all the sets, is because you also have things that are outside of the Venn diagram. So if you imagine two things that are poorly drawn, A and B, you might have 2 here, you might have 4 there, you might have 6 there. There's also the possibility of having other numbers outside of everything. This would not be considered as part of the union. The union is all of this in here. Okay, that's that. So if we look at a few basic examples, sometimes you won't get a picture with it. You might want to consider writing a picture of it just so you can, it makes it easier to just sort of see what's going on. But anyway, A is the numbers 1, 2, 3, and 7. B is all of those numbers. If we're trying to find A intersecting B, that means what's common in both A and B at the same time. So you can see 3 has a match, you can see 7 has a match, and so that's why that's the full intersection there. For the union, it would literally just be all these numbers, because it's what is in A or B or both. So it'll be 1, 2, 3, 7, 3, 4, 5, 6. So there's a bit of a duplicate there. You don't write the same number twice, you only have to represent each element once. Which, I don't know if that was explicit or not, but everything in this set of curly braces is considered an element. That's the key word for it. And you use curly braces to denote that this is not an interval. It's not like every number between these. The curly braces mean that each thing inside of it is a discrete value. So it's like, if I go to the handwritten bit, there's a couple of ways you could write brackets. You could do a set of brackets like this, you could do a set of brackets like that, and you could do a set of brackets like that. Curly braces means just 1 and 2 are the only numbers possible, nothing in between. This means all the numbers between 1 and 2, but not including 1 and 2. This means everything between 1 and 2, and including 1 and 2. So, 3 possibilities for brackets. They all behave, well, this one very differently, these two slightly differently, but the nuances do matter. Okay, one thing that comes up a fair amount is this idea of the set difference. You would usually see this written as all, yeah, the typical way that you see this written in like an actual example would be you'd have something like domain is all real excluding some number, some interval, some whatever. That backslash is technically called the set difference, but we typically think of it as excluding that. So one way of interpreting what I just wrote here was you have the set of all real numbers and you're excluding the set that is just the element 1. In the case of the book here, we've got 2 sets, A and B here. Everything in A but excluding B would mean you'd have the 1, you'd have the 2, you wouldn't have the 3 because you would have to kill the 3 because it's on both sides, and you wouldn't have the 7 because you have to exclude what's in set B. It's worth understanding the order in which you write these things matters, because what you start with, it's kind of like subtraction, right? If you do 4 minus 7, it's very different to doing 7 minus 4. What you start with will give you a better, or at least a different outcome. So if you do B removing A, we already said the 3 would disappear because it's common. 4 would stay, there's no 4 in there. 5 would stay, 6 would stay, 7 would not because of that. Again, it's kind of like whatever's the intersection, just chuck it out and you're left with whatever's left. If I need to clarify any of this, feel free to hop off mute or send a question. Okay, common sets of numbers. So the ones that will come up a lot is going to be this double-stroked R here, all real numbers. I actually wrote that in my example. Z comes up a fair bit as well. That's all the integers. So what that means is like all the whole numbers, 1, 2, 3, 4, so on and so forth, and also all the negatives of those. So 0, -1, -2, -3, so on. Those are your integers, and those are denoted by the Z. And then for N, the natural numbers, that is, it's kind of like supposed to be what you could physically count in the real world. That's what makes them, quote, natural. So natural numbers start at 1, 2, 3, 4, and shoot off to infinity. I didn't quite specify, but all real numbers basically just means like any possible number you could think of. Unless you're doing spec, in which case you could technically say a non-real number. We won't quite worry about that right now. This is very rare to come up, Q. I think, I personally think the reason it doesn't come up a fair bit is because it is hard to draw that symbol by hand. I think that's literally the only reason. But what it ends up being is all the rational numbers. As far as what a rational number is, it's just any number. So I'll go to the handwritten bit. So I'll try to do it. Q. You've got to do like this little bulge on the outside of each of them, and it just doesn't come out. It's any number that can be expressed as A divided by B. So integer divided by integer, that is a rational. So all the fractions. What's interesting is that they leave the irrationals out of this. Even though they've mentioned them in the book here, they've said real numbers are not rational is irrational. Irrational numbers are things like pi, things like √2, anything that doesn't have an ending decimal on it. Now, it doesn't have a letter per se, and this has never come up in an exam. I've never seen it come up in a SAC, but just in case your teacher likes to do strange things, one way you could potentially represent the irrational numbers is to start with all real numbers, because that's like your global everything, and you could exclude the rationals from it. And what you're left with is the irrationals. That should never come up. I just figured I'd have it in the recording just in case that somehow makes an appearance.
Is there a symbol for irrational numbers?
Yeah, so that's what I was getting at there. There is no defined symbol necessarily, at least not in the book. I'm sure there might be somewhere in Mathland, but if there was, I don't know why the book didn't put it in here. But that's one way you could describe it. All real, excluding the I think, yeah, that would get onto a tangent, but basically a lot of letters are taken up by other things, and I think people just disagree as to what an irrational should have as far as a letter rather. But whatever, that's a tangent. Something to Google, perhaps. Okay, describing a set. So what's going on here? Yeah, so we're looking at some like inequality stuff. You can use inequalities, you can use do not equal signs. You'll see element symbols, you'll see some of the natural numbers, that sort of thing. As far as the syntax, as to how this all works, let's see. So you're using these curly braces, which, yeah, I did kind of say curly braces means that everything inside of it is an element. That only really holds if all we're talking about is curly braces with just numbers in them. So in the case here, you can see there's still curly braces, yes, but you've got this full syntax in here. And so, yeah, different syntax for different outcomes, essentially. But okay, what this means is whatever on the left-hand side is your set of values, so set of x in this case for pretty much every scenario. And whatever's on the right-hand side of the colon is essentially what all the possibilities of x are. So if you said x colon 0 less than x less than 1, that's implying x can be any number between 0 and 1, but non-inclusive. Can't be 0, can't be 1. Similar going on here. X could be all numbers greater than or equal to 3. Same thing, not equal to 0. This is where it gets a little bit weirder. If you have a coefficient on that left-hand side, it essentially just means whatever's over here is still impacting your n value. So this means that n can only be the natural numbers. But whatever restriction was applied here, once you put it into your n, you also have to double it at the end. So n is still all the natural numbers. N is still 1, 2, 3, 4, so on and so forth. But because you now have 2n, what you're left with is 2, 4, 6, 8, so on and so forth. That means you're now describing the evens. And for the second one, 2n minus 1, well, whenever you subtract 1 from an even number, you get an odd number, which is why that describes all the odd natural numbers. Very rare to come up, shouldn't really ever matter. The only thing that kind of matters for using these sorts of set stuff yourself is when you're doing general solution of circular functions. So kind of like what I was talking about here, you would have to say something to the effect of n is an element of z. Now, I don't bother double stroking the z's. They should know that z is equal to the integers. That's just for people who have done that. Bit of an application as to how you might see these used yourself rather than just presented to you on a sheet. We have a few intervals. I've already kind of talked about these. They're just directly relating them to the inequalities as well. So rounded brackets means non-inclusive, which means you don't have those bottom lines. So it's just less thans rather than less thans or equals to. And I mean, yeah, that's pretty much the only interesting or different thing there. And this is considered interval notation, basically. For whatever reason, there was a printout error on this book. That's why it looks all crazy like that. That is not a glitch on your screen. So all they've done here is essentially say, hey, look, here's a set of brackets. These represent an interval. Put them on a number line. Now, I've talked about this at length in pretty much every group class. Whenever you have a dark circle, that means inclusive of that point. Whenever you have a white circle, that means exclusive of that point. So when we have -2 to 3, those are both inclusive because they're square brackets, which is why both of these are dark circles. However, when you have this situation here, a bit harder to see. You know what? I'll just write up my own one. Okay. So we have a rounded bracket on the -3, square bracket on the 4. That's going to mean starts at a circle, starts at an open circle rather, ends at a dark circle. This spot here is -3. This spot here is 4. And well, that's your full number line. Everything between those two. Everything else is just some variant of that. I guess it's worth understanding. If you have an infinity, it just means you put an arrow pointing in that direction. Positive going to the right, negative going to the left. That's all of that. Moving on to the next stuff. Relations, domain, range. So, what's worth discussing here is sometimes when they are just giving you questions which are domain, range, relations specific, they might give you weird stuff like this, which is a set of ordered pairs. Not all rules like y equals x plus 1, x squared, things like that. Not every set of points can fit nicely into a rule. Some of them are just random dotted out spots, and it's really hard to model what that is. Under those circumstances, they will give you that information as a set of ordered pairs, which just means you've got some x value and you've got some related y value. So this is the 0.11, followed by the 0.12, so on and so forth. That's all a relation ever is. It's a set of ordered pairs. It could be random points that are just sort of smashed together. It could be a relation like this, y equals x plus 1. It could have a specific rule associated with it. Basically put, any relation, anything we do as far as graphing is concerned is called a relation. It's in the bucketed term of relations. As far as domain and range are concerned, I've mentioned this in previous classes, domain is all the possible x values, range is all the possible y values after there has been a domain associated with it. So if I can only give the numbers x equals 1, x equals 3, and x equals 5, I know that the related y values there are 1, 2, 4, and 6. So my domain is 1, 3, 5. My range is 1, 2, 4, 6, which you can see here. That's for like these discrete point-based things. Other circumstances, you might have a rule. So y equals x plus 1. Now your domain still might be discrete values. We mentioned curly braces means discrete values here. And so the way you would graph that would be like over here. So when x equals 1, y equals 2. When x equals 2, y equals 3. You draw them as dots rather than a straight line through it all because of this restriction here. This doesn't mean everything in between. It just means those specific values. So even though the y values weren't told to you, you have a rule for calculating them. And that's effectively how you've been doing it all your mathematical life, basically. You get some x, you plug it in, get the y. Okay, let's see. Most of the time your domain's going to be all real numbers, so x can be anything, and that's where you get back to how you've been sketching graphs forever. You just sketch them based on whatever the key features are of that graph. This, don't worry about, this looks awful. No need to know it. Okay, and then just some examples of how you sketch things. So again, if you have a set of ordered pairs, all you do is literally dot them out on your axes. And you can see, like, these being the red dots, there's no real rule for that. They're kind of just wherever they feel like, especially this one here. It's completely vertical. It'll look like bang, 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 bang. There's no real rule to describe that. Or at least if you were to try and describe it, it would be a very big piecewise function, which we'll see a week from now, I think. Some other typical graphs, you might have seen circle before. That's what that looks like. This is just a linear after you rearrange for y. This is also just a linear. Different domains, all sorts of stuff like that. This is a very formal way of describing the relation. At the very beginning, you're essentially defining all the variables that you're using. So the reason why there's an XY here is because all the letters used are X and Y. That's really all that is. Yeah, just some pictures of that. Let's see, what else we got? Sketch the graph, state the range. Yeah, so, you've got your old graphs, whatever those graphs are. If you want to give domain, you just look at all the X values. Usually that's given to you. In this case, it's all real. And then once you have your sketch, or if you can picture it in your head, you give the range based on all the possible Y values that you can see. So we know this is a positive quadratic. It's going to be absolute minimum at the Y equals 1 here. And we know that as X gets larger or super negative, you'll shoot off to infinity. Got a question here. Can we tackle some questions from Tech Free Sac 2 that involve domain range? Yeah, we can look at those. I'll just finish up what's going on here, and then we'll go through those ones instead. Okay, implied maximal domain. This is just if there is no stated domain for your relations or whatever you've been given, you have to assume it is all the possible X values that could fit in there. That doesn't necessarily mean it's always going to be all real numbers though. So if you've seen circles before, you'll see, well, clearly anything outside of 4 or -2 doesn't really belong on that graph. This isn't a class about knowing how to sketch these though, so we'll ignore the specifics there. Point being that some graphs will not necessarily have every possible X value as their domain, so there's some effort you have to put into solving what those possible values would be. And that could be just looking at a graph you see, or using your own understanding of how to sketch those graphs. Functions. So functions have a very specific definition. If you remember from before, we were talking about like subsets of things, sets within sets. One way to think about functions is that they belong within relations. So you have this circle that I'm drawing, which is, this is all your relations are. Within that are functions. So there is no such thing as a function that is not a relation. All functions are relations, not all relations are functions. What's the difference? Well, basically put, the idea of a function is that if I know the X value, I'm guaranteed to know the Y value at that spot. So the layman's terms of that, or the easy shortcut for functions, is as long as I can pass the vertical line test, it means I have a function. The vertical line test means, I'm just going to draw some random whatever. If I can draw a vertical line anywhere on this graph and only touch it once, that is considered a function. Kinds of things that might fail this test would be like that. If you've seen this graph before, draw a vertical line. This is some X value. Let's call it X equals 1. It comes with 2 Y values. The whole point of a function, if I have 1 X, I should get 1 Y out of it. That's it, basically. You might have some nastiness here, which you've got in the screen share, which is just a bunch of different dots. Can be a bit hard to picture that. If you're good at picturing this though, feel free to just sort of, look at it and just see, do I have any duplicate X values? And if so, do I get a duplicate Y value? That's one way of doing it if you're really talented with that. The other way would literally be just to sketch and see if there's any vertical line test fails. So if I have -3, -4, it might look like that. I've got -1, -1. So far so good. -6, +7. So up here, again, so far so good. No vertical line fails. And then 1, 5. So again, vertical line anywhere on this, I'm only touching one spot. Now this will be the case in the second example, if I had 2 dots that were completely vertical with each other, that does fail it. This is no longer a function. If anyone needs me to repeat any of that, feel free to hop off the mic or leave a question. So yeah, as far as if you need a function, just do a vertical line. Domain range, we've talked about that already. Function notation, I've talked about these. What I haven't talked about is this right-hand side here. So for that, actually, I'll get up some notes. Let me grab those. Functions, relations, functions, relations. There we go. Cool. So function notation. The simplified way that you've probably seen a lot of your questions will look something like this. You've got some function called f of x and it equals something. So, f of x equals x squared plus 1. The way it works is the letter out the front is the name of the function, and whatever's in the brackets is the variable, or more specifically, the input variable of that function. Usually it's x. It can get a bit more explicit. So you might have a fully written out version here, which still has what we had before, which was name of function, variable, and the expression. The fully formal way of doing that is you rename it at the very beginning. So it could be called f, could be called g, whatever. The next thing right after is the domain of the function. So again, all the x values that could exist for that function. Next up is this thing called the codomain. I'm not even going to try and explain that because it's not in the study design and it confuses everyone. It's never shown up, so Google that if you're interested. Point being, don't worry about it. In the book, you'll always see it as pointing to all real numbers. Just it never has any impact on how you actually solve anything. But okay. So if we look at a statement like this, you've got the function called f. It has a domain of all real. You ignore that, and the function is a quadratic, x squared. You could have another example here. So again, function is called f. It has a domain of all numbers from -5 to 5, excluding 0. We ignore the codomain, and we just draw our hyperbola from x equals -5 to +5. Yeah, that's later. So when you see a couple of examples here, hyperbola has a domain of all real excluding 0. So that means all x values excluding 0. This one you sketch from 0 to 4. That's a linear. Yeah, they mention codomain in here as well. If you really want to learn it, it's there, but not accessible. They have a few examples as to how you can convert from one to the other. It's really just a matter of plugging in the spots, right? So this one has variables x and y. We can see x is the thing that's being used as an input, so you call this f of x. Domain wasn't stated, so you assume it's everything that could be in there, which in this case is all real for linear. You just slap a r in there. It's always there. All the functions we look at will have a pointing to r in that. So just give that as a default. And then yeah, I mean that's the gist of it really. We look at anything else. Yeah, that's about it. If anyone wants me to dive into any more of that in detail, let me know. Otherwise, I'll pull up one of the SACs that I have and we can look at some exam style questions for this. Okay, tech-free SAC 2. If you had any questions specifically on that you want to look at from that SAC, let me know. Otherwise, I'll just sort of pick them out myself. Tech-free SAC 2. Okay. Yeah, let's see what we got. There we go, maximal domain. Cool, straight up, off rip. And this one actually is a VCAR exam specific. I pulled this from a past exam. Which one specifically? Not too sure, but wouldn't have been too old. Okay, I'll just start writing it down. So we have our function, which is f of x equals natural log of x squared minus 2x minus 3. What you'll find with all this domain range stuff, the functions and relation style stuff, is that it very much requires you to actually understand what functions are even being talked about in the first place. It's never a standalone thing necessarily. So you really have to have a deep understanding of logarithms, exponential, circular functions, linear, quadratic, polynomial, all the base graphs that could be possible. But okay, this one here is maximal domain of this function. So whenever you see the words maximal domain, It's basically saying, what are all the possible x values that could fit into this function? Now, it doesn't look like a standard function. It's natural log of a quadratic, a bit odd. My recommendation for when they do weird things like this, when it is a bit confusing, is just simplify the whole process and just say, okay, well, what is the basic version of this? If I just had like some natural log of u, whatever goes in there, just some bare bones basic logarithm, what are all the possible x values of a basic logarithm? Those who know could answer, otherwise I'll just sketch an example logarithm. And someone can tell me what are all the possible x values of a function like this.
Is it all natural numbers excluding zero?
I like what you started with. So natural numbers. So basically, natural numbers are like discrete is the only issue, like 1, 2, 3, 4, so on and so forth. We also want to include everything between 1, 2, 3, 4, and all that.
So maybe all positive real numbers?
That's exactly right. So one way you could say that is x is an element of r plus. You can put a plus there for only positive real. You could use interval notation. You could say 0 to infinity. Again, not inclusive of 0. That's just a specific quirk of the logarithm. You can't have 0. So now that we understand how a basic logarithm works, it doesn't actually matter what we put in here. We still just need to make sure that whatever this is between 0 and infinity, not inclusive of 0. So now the question boils down to, okay, how do I make sure that everything in here is greater than 0? So we just move on to the next bit, which is, okay, I have my x squared minus 2x minus 3, and I need to make sure that is always greater than 0. How do I do that?
You solve for x in terms of inequalities?
Yeah. Yeah, we solved the inequality, sure. Question now becomes, how do we do that? What would the next line look like, perhaps?
Could we factorize it into x? Like, could we put into factorization form?
Yeah, let's see. Do we have a factor?
Minus 3m plus 1, x minus 3, x plus 1.
Yep, that looks good to me. Yep, good start. How do we then?
And then with null factor law, we can just say that x is greater than -1 and positive 3.
Yeah, so I like what you've done.
Sorry, since it's x has to be greater than 0, then the only like value that makes is 3.
Sorry, so repeat that last bit.
I mean, since we've got like 2 values, right?
Yeah.
But we had to have like more than 0, then it would be x is more than 3.
Yes, so what you're saying
That's the
is
value we accept.
you're saying cut this one off and then that's your final answer?
Yeah.
I like your idea. The only challenge here is it's not a stock standard null factor law here, because when you're doing inequalities, you are allowed to have things that are positive, not necessarily just equal to 0. And so what ends up happening, so if we just did x greater than 3, that would still be positive, right? Everything, so you can see if I plug in x equals like 4 here and 4 here, positive times positive is positive, we're all sorted. But what's also possible is, if you think about how, like if I have two numbers a and b that multiply together, they can give either a positive or a negative. Greater than 0 just means I only want these to be positive. And there's two ways you can do that. You could have them both positive or both negative. So one potential way of doing that is what you've done here, but you don't ignore this. This matters. You also want to figure out not only where are both positive, or are both negative as well. That's one way of doing it. It does take a while though, and I wouldn't recommend it. It can be a bit confusing. What is better is the fact that we all know how to sketch this, or at least we should know how to sketch this by now. If we have it in a factorized form, the null factor law, which we already did, tells us where our intercepts are, and the fact that it's a positive quadratic means it's going to look something like this. We don't even care about the turning point, really. Now, the advantage of having sketched this is that now this thing that we just sketched is y equals x squared minus 2x minus 3. And saying this is greater than 0 means we want all the y values to be greater than 0. So we care about all of this and all of this. So x greater than 3 was what you found in the beginning, which is good. The thing about going straight to say x greater than -1 is that, well, it was kind of that weirdness that I was talking about before, which is this isn't really null factor law. It's pretty close, but not quite. So it ends up being the case that what you actually care about is x greater than 3, yes, but also less than -1. That becomes the final answer there. So do I need to repeat? I mean, that was a fair few steps there. Is it clear the progression from start to finish? Well, you guys have a think about that. I'll find another question.
So what would you write? Like, if you had to answer this, would you just draw and like sketch that, or would you write something?
Yeah, so you would end up writing something at the end, which would be, you have a lot of ways of expressing this. My favorite is just to not think too hard about it and just say, okay, well, there's my negative infinity and it ends at -1, making sure I'm doing rounded brackets because I want to be greater than 0, not equal to. And use my union symbol to join the second part, which is 3 to infinity. It's longer, but at least it's like very visual. I see that interval, I just smash them together. That's one way. The other, if you guys want to reduce the amount of time you spend writing, is to, instead of saying what's included, you start with everything, so all real, and you kill what's on the negative, or what's on the inside. So you would exclude -1 to 3, this time inclusive, because you're saying what's disappearing. So this can be more complicated to think about, getting the brackets right around there, but it's also faster. Barely. So it's up to you guys how you want to write your answer. Both of those are equivalent. Fair enough on how you'd finish up that question.
Yep.
Okay, what else we got? Different domain stuff. I mean, like, there's a lot of questions that have domains in them. It's hard to say, like, what specifically you were looking for, Upraj. That one's more so transformations, though. It's a bit out of scope. This has also got... Yeah, this is the same sort of vibe. Question 3, at least up until part B, for inverses. Okay. So, starting from the top, again, we got a logarithm over the maximal domain. So this will be a quick bit of revision. We had 2 natural log of 5x, and -2 out the out. And it's defined over the maximal domain. So I'll zoom out a touch just so you can see what we did for that before. This is still the same kind of graph. It's still a logarithm, still going to look roughly like that. What would the maximal domain of this be? use this as your base graph to compare to. So remember, start by ignoring whatever's in here. All this external stuff we can ignore. And just focus on this graph. We know just by looking at that, we start with all real positive. And then all you do from there is say, okay, whatever's inside the brackets, how do I make that all real positive? What is that? What actually changes, if anything?
Is that just like a dilation factor?
Yeah, just dilator factor. So what does that actually mean for our domain? Does anything change?
I don't think so.
Not at all, no. So yeah, if I were to sort of go through the same process, you know, if you guys are relatively new to these functions, again, start with this and you say, okay, at a base level, any basic logarithm is going to require us to have all real positive for our domain, or whatever's inside the brackets. So we start with x as an element of all real positive, but we have 5x. So we need to figure out what's going to take for 5x to fit into all real positive. Well, we don't actually have to do anything. Whether you're comparing to x or whether you're comparing to 5x, these already both contain all real numbers in them. So there's nothing crazy to be done. The only reason we have to do something with the quadratic is that it can go negative. So there are portions of it that become, there are possible values of this that become negative. So with this one, you're still just going to cut these linears off here, and they're still going to be just all real positive. There isn't like a dip over here that would cause it to become negative again. Okay, that's that. There is inverse in here. There isn't a whole lot of time for it, so what I'll do is I'll jump back to the questions here, and we will just have a look at. Yeah, they don't actually have any maximal domain questions here. Well, let's find them. Yeah, here we go. Okay, so we've done logarithm ones already. We know how those work. Next up is the square root type graph. So I'll just make up my own one, I guess. Square root of 2x minus 1 is our function. So again, we're going to treat it similar to how we treated the logarithm. We start by figuring out, or at least trying to understand, what is the basic version of this graph look like. And the very basic version looks like this. What are the restrictions on this kind of function as far as the x values are concerned? This one being the simple one.
X is all positive real numbers,
Pretty close. So
and including 0.
And including 0, yeah. So one thing to keep in mind, real positive does not actually include 0. So if you do use that notation, you have to put a union, curly braces, 0. That's, you know, one little pitfall of being overly reliant on the real number symbol. So another way you could do it is just say x greater than or equal to 0. You could say 0 to infinity. Any of these are, you know, if you know what you're doing, obviously do whatever, but this is safest. Don't have to think too hard. Okay, so we know the basic understanding of how the root works. We just need to make sure that whatever's inside the root is positive or 0. In this case, we have 2x minus 1. That has to be positive or 0. So we have our 2x minus 1 greater than or equal to 0. I know all of you can solve that inequality. Equal to 1, x greater than or equal to a half. That is the maximal domain. You can give it as the inequality, just like that. You could give it as an interval, like this. If you do, be sure to use x as an element of that thing. Even if you don't, most teachers will let that go. Even the assessor should let that go. But this is technically more formal. Yeah, I mean, that's about it there, really. You could write this different ways, but then you're just getting really absurd for no reason. Okay, that's one type of function. Next one Yeah, they have an example of it. So hyperbola. Let's grab up one of those. So say 1 over x take 2. Why not? 1 over x take 2. That's our function. We want to know what is the maximal domain of this. So all the possible x values here. I will start by sketching the basic version, and then we can again use that technique where we contrast that to what the one we have to handle is. That's the basic hyperbola. It has asymptotes at y equals 0 and x equals 0. So what would the maximal domain of the basic version of this be?
Chris, is the maximal domain to the same as the x values?
Yeah, all the possible x values of the function.
So then would it be all real numbers except 0?
All
Because
numbers
it's just all real numbers?
wait, sorry, say that last bit again then?
Would it just be all real numbers because 0 isn't included in real numbers?
So, okay, the nuance on that is what I mentioned before was that 0 isn't positive. That's what I meant before. So when you say all real positive, you have to say union 0 because 0 isn't positive. 0 is a real
Okay.
number though, so that's the difference there.
Then is it all real numbers excluding 0?
Yeah, that's better. Yeah, so all real numbers excluding 0, that's the basic bit. Now, very simply, if you just look mathematically, if you think about plugging in some values in your denominator there as x, if you divide by 0, you get an asymptote. It's not great. So in a real way, there's only really a few things to watch out for, which is divide by 0 errors, what would cause it to divide by 0, or when it comes to fancy stuff like roots and logs, you just want to make sure you're positive, or sometimes including 0, sometimes not inclusive 0, depending on the function. But okay, so we now know that this denominator can never be 0. What's the only bad x value that would cause denominator to be 0?
2.
Yeah, x equals 2. So when we give our domain, that's the only one we don't want to have. How do I write that as a final answer as far as domain is concerned?
X is an element of all real numbers, excluding 0.
Perfect. Bang on. That's the fastest way of doing that. Again, you could use intervals, you could use inequalities. Personal preference, really. Okay, that's hyperbolas. What else? We've done that. Truncus is the same deal. Doesn't matter if it's squared, cubed, or anything on the denominator. Anything that has a division in there just still can't be divided by 0. So even if I had like 1 over x to the power of 10, it's still just, we don't want to have that. When it gets a bit more interesting is when you have like multiple things to keep track of. Like for example, one that I'm spotting there is 1 divided by root x. That's not typical necessarily, so it'd be pretty hard to draw a basic graph of that if you haven't. Well, hard is relative, but this isn't a graph you've been necessarily taught. So if we put together the basics of what we've been discussing, what kinds of things are worrisome when it comes to potentially bad x values? What do we want to avoid? If you were to give me a potential x value that would cause this to break, that's another like a decent question to ask. It's just, what could I put into this function to make it like break, mathematically speaking?
Any negative number,
Yep, all the negatives are bad. Why is that?
because you can't have a negative square root.
Very good. So already we've ignored all the negatives. Okay. What else is bad about what we've got here?
Maybe 0 as well.
0, yeah. So even though the square root would be fine with 0, The fact that we're dividing by 0 is still the issue. So basically, yeah, bring it up into the individual parts. You got division, so dividing by 0 is bad. You've got root, so any negative is bad. I could have a similar thing, like 1 over natural log of x. It's now, okay, now I definitely can't have 0 or negatives, so, well, it ends up actually being, oddly enough, these have the same maximal domain. So, no zeros, no negatives. What am I writing as final answer for that?
All real positive.
Yeah, all real positive. That's good. It's the simplest way to write that, or at least the fewest number of symbols to write that. Okay. I just noticed you've rejoined. That's all good. We had a look at a composite function, essentially. So the idea behind that was just what happens if you have multiple functions on the same thing. You're essentially looking at, okay, I have square root, so can't be negative. I have divide by 0, so can't be 0. You're basically just marrying those two concepts together. So if you have these more complicated functions that you can't necessarily sketch, this is how you achieve that. Everything else just has like slightly different looking graphs. So even if I were to go through, like this one technically, this square root semicircle, you could technically draw as a semicircle. Most people don't really teach this in school though. So how you handle this is still going to be the same as how you handle any root. We know that anything inside the root has to be positive or 0. And so you would then, again, as before, just grab whatever's on the inside, make it greater than or equal to 0, and solve from there. That's if you don't know this is a semicircle. If you do, then by all means, just draw the semicircle. For example, this would be a radius of 4, and there's no translations involved. So starting at 0, out to positive 4, out to negative 4, and because it's negative, you give the bottom section of that. We can clearly see it's from negative 4 to 4. If you don't know that, that's fine. You can just draw the graph of 16 minus x squared, and you cut off all the possibilities that cause you to go negative, which would be anything left of here and right of here. You can see it's the same situation. Now, I didn't get into the specifics of why this is 16 minus x squared, but that is just sketching a quadratic. You guys should be able to do that at this point. So either approach will get you there, whether you know or don't know. That's a semicircle. Okay, I mean, that's about it really. 2 minutes doesn't leave a whole lot of time to discuss anything else as far as content goes. But as far as where you can practice these things, well, we've been doing chapters 5a through d, essentially. So there's a whole bunch of ways you could practice that. 5d does have this slightly new thing, which is a one-to-one function. It's not so crazy. So it's kind of like how I said in the beginning we had this diagram here where functions were a subset of relations. You now have one-to-one functions, which are a subset of functions. 1-to-1. And just very briefly, what that would be like is instead of just passing the vertical line test, you also have to pass the horizontal line test. This one does not pass. Something like a linear does. Any line that I draw there will only touch it once. That's the only new thing for this 5D here. So 5A through D, practice those if you're up to it. Give the opportunity to seal that knowledge in. Any final questions, feel free to stay behind. Otherwise, I'll let you enjoy the rest of your lives. Until the next lesson. Thanks, guys.